Hey everyone, so now we are on to our last video in Unit 11, our last video for the year. This is Lesson 2 on equilibrium. We're also going to be discussing something called Le Chatelier's principle, which is very important when discussing how a chemical system that's at equilibrium, how it responds when it is introduced to some type of stressor or some type of change. So let's take a look at reversible reactions. So in a traditional reaction, all of reactants get turned into products and don't go backwards. However, a reversible reaction is one in which the conversion of reactants to products and then the conversion of products to reactants happens simultaneously. So the reaction can literally go forwards from reactants to products, or it could go backwards where the products are turned back into reactants. So that is a reversible reaction, and an equilibrium reaction is a special kind of reversible reaction in which the rate at which the forward and reverse reactions happening occur simultaneously at the same rate. So if we took a look at a graph of concentration of reactants and products versus time on the same graph, where the green and the red represent the reactants, you can see they're going down with time, and the yellow represents products, you can see that it is going up with time. They seem to stop partway through before all the reactants are used up. So this is not the same thing as saying the reactants are running out. In this case, like we saw for kinetics graph back in our last unit. Instead of the reactants getting used up, all of the reactants are getting turned back into products. So in this case, when the line goes flat, it doesn't mean the reactants are being consumed. It means they no longer appear to be changing because the reaction is at equilibrium. All of the reactants are being turned into products, and then all the products are immediately turned back into reactants. So at this point, the reaction is said to be at equilibrium, which is indicated by this darker shaded portion right here, whenever the concentrations of all reactants and products appear to be steady. And you can see that the reactants have not quite been used up, because if so, then this line would be at 0 for the reactants, but they're not. So at equilibrium, the concentrations of products and reactants no longer change. So in this reaction, we have an example of sulfur dioxide combining with oxygen gas to form sulfur trioxide. So you can see that once equilibrium has been established, as soon as the sulfur trioxides have been made, they are turned back into sulfur dioxide and oxygen. So even though it seems that the reaction has stopped, according to the graph, you just see a flat line, the reactions are still happening. It's just they're happening at equal rates, so it appears that nothing is happening. So the rates of the forward and reverse reactions are equal at equilibrium. So let's not forget that this is all happening in the same system. It's not like there are two different systems, one with reactants and one with products. It's all happening in the same system. It's just a little bit confusing to look at it that way because we can't differentiate between products and reactants if they're all in the same system. So just keep that in mind. They are happening in the same system. And it is something called dynamic equilibrium. So I'm going to give you an example. If you're looking at an escalator, and if you're looking at the rate of shoppers going up the escalator and going down the escalator, so if you have the same rate of customers going up the escalator and the same rate going down, then it appears that the number of customers on both the first and second floors are constant. It seems like they're not changing, but they really are. They're just changing at equal rates. So this is called dynamic equilibrium, whenever the rates of forward and reverse reactions are equal. Equilibrium, in which this is happening in a chemical reaction, is an example of dynamic equilibrium. Dynamic equilibrium can occur in lots of systems, not just those that have chemical reactions. So dynamic equilibrium specific to a chemical reaction is called chemical equilibrium. So let's take a look at a summary of what we have talked about. At chemical equilibrium, remember the rates of the forward and reverse reactions are equal. So it appears like the reaction has stopped, but it really has not. And it's where the lines of reactants and products have become flat. So again, this does not mean that the reaction has stopped. It just means the forward and reverse reactions are happening at the same rate. It also doesn't mean that the concentration of reactants and products are equal at equilibrium. Okay, it just means they're no longer changing. So if you take a look at both reactants, you can see that their equilibrium concentrations are different, and they're much less than the equilibrium concentration of the product right here. So remember, equilibrium doesn't mean equal amounts, it just means equal rates. So you can see at equilibrium, there is much more product, this sulfur trioxide, as opposed to the sulfur dioxide and oxygen, which is why you see much more of the sulfur trioxide here in the box on the right. So I've introduced how to write equilibrium equations when we were talking about acids and bases, and so they're indicated by that double harpoon arrow. So each of the arrows only has a single sided head, and so the one where it is going upwards is indicating reactants being converted to products, and then the backwards arrow with the hook going down is indicating that the products are turning back into reactants. So you're going to see a lot of the time when we're talking about just the arrow to the right with the hook going up, that is indicating the forward reaction. So the reactants are becoming products. And if you see the arrow getting larger, that means more reactants are turning into products. So the reactants are going down and the products are going up. If you see the arrow to the left with the hook going down, that indicates the reverse reaction or the products becoming reactants. And again, if you see that line getting bigger on the bottom, that means more products are being converted into reactants as opposed to reactants into products. So let's look at a practice problem on equilibrium that you might see on an exam. So let's look at these sequence of diagrams, and they represent the system as time passes for a gas phase reaction in which reactant X is converted to product Y. You can see reactant X is denoted by the black dots, and product Y is denoted by the white dots. So which statement is correct? Okay, so let's look at our options here. So we can see the diagram at 7 seconds, it is all reactant. Then at 5 minutes, you see some product being made. And then at 10 minutes, you can see a couple more product being made. And then at 5 days, the difference between 10 minutes and 5 days diagram is exactly the same. There's still 4 products and 1, 2, 3, 4, 5 reactants. So not even looking at the options here, I would assume that this reaction has reached equilibrium after 10 minutes. So your option C, at t equals 10 minutes, the system has reached a state of equilibrium. That's the answer. I don't even have to look at the other choices. That is the correct answer. Let's look again at this example reaction. So we have 2 sulfur dioxide molecules combining with 1 oxygen to form 2 sulfur trioxide molecules, where the sulfur dioxide is represented by the green, the oxygen by the orange, and the yellow with the sulfur trioxide. So you can see that the sulfur trioxide at the start of the experiment is 0. There is no product. However, we're starting with 2 molar sulfur dioxide and 1 molar oxygen gas. And you can see over time both the oxygen and the sulfur dioxide go down and the sulfur trioxide goes up until it reaches equilibrium about right here when all 3 lines level out. So let's look at another situation. What if you only start with product? What if you only start with product and no reactants? Remember, this is a reversible reaction that will achieve equilibrium at some point in time. So because it's an equilibrium reaction, if you only start with products, then it makes sense that the reverse reaction will start going first, right? Until we have some reactants made. So you can see the sulfur trioxide going down and then the sulfur dioxide and oxygen gas going up. Again, until equilibrium is reached, in which case the forward and the reverse reaction rates are equal. So a system will reach equilibrium whether you start with reactants or products or a mixture of these. So again, the reversible reactions will tend towards equilibrium regardless of the initial concentration of reactants and products. And the position a reaction reaches at equilibrium can be expressed as the equilibrium constant denoted by Kc. You'll see this is a little bit similar to the equilibrium of water, or the ionization of water, when we said that water would dissociate into hydrogen and hydroxide ions, and that was represented by Kw. That is because the ionization of water is an equilibrium reaction. So the rate at which it dissociates is equal to the rate at which it reforms water, and that's what the Kw meant. It was actually the equilibrium constant of water. So just for anything else, it is denoted as Kc, C for concentration. You won't be responsible for knowing how to calculate these at this point in time. I just wanted to introduce to you. So if you see a K value, that means that is the ratio of products to reactants at equilibrium. If it's a really large number, it just means there's a lot more products than reactants at equilibrium. And if it's a really small number, it just means there's a lot more reactants as opposed to products. And again, so starting with no products or starting with no reactants, again, equilibrium concentrations should be equal, right? So you can see the equilibrium concentrations of all three are going to be equal regardless of how much you start with. This brings us into Le Chatelier's principle. This describes how a dynamic chemical equilibrium responds to disturbances, or if a system is changed in any way, the way a system reacts can be predictable, okay? So it states if a stress is applied to a system that's already in equilibrium, the system will change in a way to minimize the stress. It wants to go back to equilibrium no matter what. So it's going to do whatever it can to get back to equilibrium. This applies to changes in concentration, pressure, and temperature. So again, let's take a look. We're using our typical, sulfur dioxide, oxygen makes sulfur trioxide gas. You can see we're starting again with 2 molar sulfur dioxide, 1 molar oxygen, and 0 sulfur trioxide. And we see our typical equilibrium ratios that you've seen in previous graphs. So equilibrium is established. And just so you guys know, the equilibrium constant for this reaction is 18.15. So there's a lot more products at equilibrium than reactants, as we already saw with this reaction. Okay, but what if we stress the system out? Okay, it is at equilibrium. These are its equilibrium concentrations that we saw. What if we add a lot more reactants, specifically sulfur dioxide? So its equilibrium concentration is 0.6 molar. But say we bump it up to 1 molar. What is that system going to do if we suddenly increase the amount of sulfur dioxide? It's like, hey, this is too much. This is more than we're supposed to have. I need to get rid of this. So what's going to happen is the system is going to make a lot more sulfur trioxide than it normally would because it wants to get rid of that extra reactant. So you see how this equilibrium arrow, the forward reaction, is getting bigger? That's because equilibrium has been disturbed. It's not in equilibrium anymore. All of a sudden, it's going to start making a lot more product. So you see the amount of sulfur trioxide go up, and then the amount of both sulfur dioxide and oxygen is going to go down in order to reestablish equilibrium. And then equilibrium is going to be reestablished. The exact same ratio is going to be reestablished. It just so happens that the ending concentrations of our reactants and product are going to be a little bit different than they were before. However, the ratios are going to be exactly the same. So let's have another example. We're disturbing this system. So it's at its new equilibrium, but then we remove all of the oxygen. All of a sudden, there's no more oxygen here. Uh-oh. Equilibrium is being disturbed. Well, we need some more oxygen in here, right, to keep our ratios the same. So what is the system going to do in response? Well, all of a sudden, the reverse reaction is going to become more prominent. So this bottom arrow is getting bigger because, hey, I need to make some more oxygen to compensate for the loss. So I'm going to shift. It's called shifting to the left. I'm going to shift to make more reactants. So then I'm going to have my sulfur trioxide go down a little bit because it's being used up to make some more oxygen. And then I'm going to see both oxygen and sulfur dioxide go back up until I get the same equilibrium ratio. If I take the ratio of reactants to, products to reactants, I'm going to get the same equilibrium constant. Okay, so equilibrium again is reestablished. Let's look at another example of a disturbance. Okay, this time I'm going to add a lot more product, sulfur trioxide. So it was at 1.381 molar and I bumped it up to 2. So I injected some more sulfur trioxide into the system at this point. Again, the reaction is going to shift to get rid of that extra sulfur trioxide, and it's going to shift the reaction to the left. So I want to remove it. So the sulfur trioxide is going to go down. The sulfur dioxide and the oxygen are going to go back up again until my equilibrium constant is reestablished. So again, my equilibrium concentrations are now a little bit different. My ratios, the same. So now one more disturbance. Let's say I now remove sulfur trioxide. The system is disturbed by the removal of a product, so it's going to compensate, according to Le Chatelier's principle, by making more of that product. So now my reaction is going to shift to the right. I need to make some more product to compensate for the loss. So you can see that the product is going to slowly go back up. The reactants are going to go down until that equilibrium again is reestablished. And this is a predictable thing that every system is going to do if it's already in equilibrium to respond to a disturbance. It's going to shift and change in predictable ways. So again, equilibrium reestablished. So again, this is called shifting a reaction. And again, it only is applicable to reactions already in equilibrium. So if you see the top arrow becoming bigger, that means the reaction is shifting to the right. It's making more product until equilibrium is reestablished, and then again, those arrows are the same size. If you shift to the left, like for instance, you remove a reactant or you add too much product and the reaction shifts to make more reactant, that's called shifting to the left. And in this case, the bottom arrow will get bigger until equilibrium is reestablished, in which case then they will be the same size again. So basically the size of the arrow is representing if it's going towards one direction more so than the other. So what happens if there is a change in concentration? So if the reactant concentration is increased, then the reaction is going to shift to the right to make more product until the equilibrium constant is reestablished. If the reactant concentration is decreased, then more reactant is going to be made. The reaction will shift to the left in order to make more reactant. So that is the response until equilibrium is reestablished. If the product concentration is increased, then the reaction is going to again shift to the left in order to make more reactant and to get rid of that excess product until, again, equilibrium is reestablished. And then lastly, if the product concentration is decreased, it's removed, then the reaction is going to shift to the right to make more of it. So it's going to shift in a way to counteract the disturbance according to Le Chatelier's principle until equilibrium is reestablished. So let's look at a multiple choice question here. The manufacture of sulfur trioxide can be represented by the following equation. We've already talked about this. If sulfur trioxide, the product, is removed when the system is at equilibrium, then what's going to happen? So if we get rid of this, then the reaction is going to want to shift to the right to make more of it. Again, until equilibrium is reestablished, and so that will not change. The system is going to shift towards the products, and the equilibrium constant will not change. So D is the correct answer. So not only will a system respond to changes in concentration, but it also responds to changes in pressure. So let's look at this typical reaction. This is one we've seen before, the synthesis of ammonia called the Haber process. We have nitrogen gas plus hydrogen gas makes ammonia. So we want to label the side of the reaction with more gas molecules as higher pressure and the side with fewer as lower pressure, because if there's more molecules on the reactant side, then the pressure will be higher on the reactant side. So we have 4 molecules of gas on the left and only 2 on the right. So the gas molecule on the left is going to be this is 4 and this is 2. So this is going to be the higher pressure on the left and lower pressure on the right. So if this system is at equilibrium, okay? Equilibrium, the rates of forward and reverse reactions are happening. If the reaction, all of a sudden, we increase the pressure of this system, the reaction can't really counteract this if it's in a closed system. Like it can't all of a sudden make a bigger size container. So what can it do? The only thing it can do is shift to the side with less gas molecules that has lower pressure. So this is the only way to counteract the pressure increase. If we decrease the pressure of this system, then the reaction is going to shift to the side with more gas molecules, so to the left, in order to increase the pressure again. So again, the equilibrium constant is not affected. The system is just going to adjust until the equilibrium constant is once again established. So let's look at an example of the Haber process. We have 3 containers here, and you can see that they are all at the same pressure, 100 kilopascals, and they all have the same amount of gas molecules. They have 11 gas molecules total. Okay. So let's increase the pressure of the system on the left, okay? So the pressure is increased to, looks like, I don't know, what is that, about 150 kilopascals, okay? And then the one in the middle stays the same, and the one on the right, we decreased the pressure. So how is the system going to counteract and respond to this both increase and decrease in pressure? Well, the container that has higher pressure, it's going to want to shift to the right because the product side has less gas molecules. So it's going to shift to the right until equilibrium is reestablished. So it's going to be using up some more reactant molecules to make this NH3 because there's less molecules of gas that way. So now instead of having 11 gas molecules, it has 9. So the pressure is going to be reduced in this scenario, counteracting the disturbance. So you can see how the pressure is going down now. And again, it might not get to the original pressure. It's the best that the system can do in this scenario, but it's still not going to affect the equilibrium constant because the ratio of products to reactants is still going to be the same in this case. Okay, so what about the system where we decreased the pressure? So since the pressure has been decreased, the only thing the system can do is shift to the left because that side has higher pressure. It has more molecules of gas. So it's going to get rid of the ammonia and make some more hydrogen and nitrogen gas. So now, instead of having 11 gas molecules, the system will have 13. And in that case, that is going to increase the pressure of the system in order to counteract the disturbance. Again, equilibrium constant is not changed. So let's look at a multiple choice question here. So we have our sulfur dioxide and oxygen system making sulfur trioxide. How is the amount of sulfur trioxide and the value of the equilibrium constant affected by an increase in pressure? So we have to again look at the number of molecules on each side. We have 3 molecules of gas over here and 2 molecules of gas on the right. So the higher pressure is going to be on the reactant side and the lower pressure is going to be on the product side. So if we increase the pressure, the system is going to want to shift to the right to counteract that increase in pressure. So the amount of SO3 is going to increase, but the value of Kc does not change. Remember, changing concentration or pressure does not change the value of the equilibrium constant. One of the very last factors we're going to look at is the effect of changing the temperature on equilibrium. So you remember that a chemical equation that includes heat changes or enthalpy changes is called a thermochemical equation. And remember, the sign of the delta H indicates what side that the heat is going on. So if it's negative, it's exothermic, and that enthalpy is going to be placed on the product side. If it's positive, we're going to put it on the reactant side because it's endothermic. But remember, the sign is always positive in a thermochemical equation. It's just going to be on the left if it's reactants, if it's endothermic, and it's going to be put on the right if it's a product of it's an exothermic reaction. So for example, in the process of making ammonia, it is an exothermic process in which 91.8 kilojoules of heat are released. So we're going to write that as 2N2 plus 3H2 makes 2NH3 plus 91.8 kilojoules. So if we wanted to write the following thermochemical equation, iron chloride dissociates into iron and chlorine gas. You'll see our delta H is positive 342, so I'm going to write that as a reactant. Plus 342 kilojoules makes iron and chlorine gas. And there we go. Just a brief reminder of how a thermochemical equation is written. So now I want you guys to write the following equation as a thermochemical equation. So nitrogen dioxide gas is converted into dinitrogen tetroxide. It's exothermic with negative 57.2 kilojoules being released. So I want you to label this side with heat as the hot side and the side without as the cold side. So by an H or by a C. And so if the temperature is increased in this system, that's exothermic, the reaction is going to shift to the cold side always, because the only way that it's going to counteract the increase in temperature is by shifting to the side that absorbs heat, the cold side. And remember, if it's an exothermic reaction going to the product side, then if we shift and go to the reverse reaction, it's going to be endothermic, going from reactants to products. So if this is an exothermic reaction, the reaction is going to shift to the left if we increase the temperature, because that's the only way that it's going to be able to absorb the excess heat that we put in the surroundings. Likewise, if we were going to decrease the temperature, so if we make the surroundings colder, this is an exothermic reaction, it releases heat. So how does it counteract a decrease in temperature in the surroundings? It's just going to make more heat, right? So it's going to shift to the right and just release that heat because it is exothermic. So it's going to shift to the hot side. In this case, the equilibrium constant is changed, okay? That is because the rate of the reaction is now changing. If it's an exothermic reaction and we lower the temperature, the forward reaction is going to be happening at a much quicker rate than the reverse. So in this case, the equilibrium ratio of products to reactants will in fact be different. Remember, changing the concentration or the pressure does not affect the equilibrium constant at all. Changing the temperature does. So let's look at an example of this. Okay, so we have nitrogen dioxide gas, which is brown, and then the dinitrogen tetroxide gas is colorless. So you can literally see if the reaction is shifting more towards the reactants or products by looking at the color change in this flask. Okay, so we're going to determine if the flask will turn more brown or more clear if the following disturbances occur. Okay, so it is an exothermic reaction. It's going to release heat. So if we increase the temperature, it is going to want to shift to the left to absorb the excess heat. So it's going to be more brown. Will the Kc change? Yes, it will. So if it shifts more to the left, that means our Kc is actually going to decrease because the amount of products is going down. If the temperature decreases, then it's going to shift to the right to make more heat. Remember Le Chatelier's principle, it's counteracting any stress. So it will turn more colorless. And in this case, our Kc will change, yes, because temperature affects it. And if we have more products than our at equilibrium, then our Kc will be higher than normal. Okay, what about pressure? So this is a gaseous system, so pressure can definitely have an effect on equilibrium. If changing pressure doesn't really have an effect on non-gaseous systems because, solids and whatever are usually at constant pressure. So increasing the pressure is not really going to change that too much. So if we increase the pressure on this system, because it is a gaseous system, it's going to want to shift to the side with less pressure, less moles, which is the products. So it's going to turn colorless because it's going to shift to the right in order to reduce the pressure. Will the equilibrium constant change? No. Remember, pressure and concentration do not affect it at all because the ratio of reactants to products at equilibrium will still be the same. Okay, so then pressure decrease. It is going to want to shift to the side with more molecules, which is the left side. So it's going to turn more brown. Will the equilibrium constant change? No, it won't. Volume increase. Okay, if we increase the volume, that's the same thing as decreasing the pressure. So it's going to do the exact same thing as if we had a pressure decrease. And again, the equilibrium constant won't change. So volume decrease is like increasing the pressure. So it's going to shift to the side with less moles of gas. And no, the equilibrium constant will not change. So let's look at what will happen to the position of equilibrium and the value of the equilibrium constant when the temperature is increased in the following. Okay, so let's look at bromine gas plus chlorine gas makes 2 bromine chloride, or yeah, bromine chloride gas. The delta H is positive, so it's an endothermic reaction. So if we increase the temperature to something that absorbs heat, right, it is going to want to shift to the right in order to absorb the excess heat. It's endothermic. So I'm going to make more bromine chloride product whenever I increase the temperature. So the position of equilibrium, it's going to shift towards the product. So the answer could be either C or D. So if I make more product, I have more product in the numerator, because remember our equilibrium constant is a ratio of products to reactants. So if I make more product, then my equilibrium constant is going to go up. So again, my answer is D. Going to shift towards the products and my equilibrium constant is going to go up. Our last condition, if we add a catalyst, how does that affect equilibrium? So equilibrium constants are not changed at all if you add a catalyst. It also doesn't change the position of equilibrium. It's not going to shift left or right either. That's because catalysts don't play favorites. They shift both the forward and the reverse reaction equally by the exact same amount. So it's going to speed up the time it takes for a reaction to reach equilibrium, but it's not going to change the equilibrium constant, and it's not going to shift left or right because both the forward and reverse rates are increasing equally. So the only thing that changes an equilibrium constant is temperature. So let's look at a chemical energy diagram of something that's exothermic. You can see reactants being converted to products. Again, you see our delta H is negative, and we see our activation energy right here. So adding a catalyst lowers the activation energy by providing an alternate route. So the activation energy is lowered, but it's lowered for the forward and the reverse reactions equally. So nothing changes, nothing shifts, the equilibrium constant does not shift. So you can see both arrows are getting bigger, but equally. And our last question, so it's about a catalyst. We have the manufacture of sulfur trioxide here. What happens when a catalyst is added to an equilibrium mixture from this reaction? So the rate of the forward reaction increases and that of the reverse decreases. The rates of the forward and reverse reaction increase. Boom. They both increase. It doesn't change our enthalpy change. It doesn't change our yield of anything. It just increases the forward and reverse rates equally. All right, guys, that is it for our last lesson. I had a really good time making these for you this year, and I hope they were helpful. And I will see you in class. Bye.